Hello and welcome to my virtual on-demand session about the Medik8s project, which consists of multiple components which serve as a medical toolkit for your Kubernetes cluster. A few words about myself. I'm Marc, Principal Software Engineer at Red Hat. I started my professional career in 2001 as Java consultant. In 2015, I worked on a research project about distributed applications where we investigated Docker and early versions of Kubernetes, and shortly after that I also implemented first components in Go. I liked this combination of Kubernetes and Go so much that I looked for a job where I can do more of this and found it in 2018 at Red Hat. Since then, I have been working on multiple so-called operators for Kubernetes and OpenShift. Before I introduce the Medik8s project, let me take one step back and do a quick and very simplified recap about how Kubernetes works. It's basically all about a declarative approach of deploying workloads on clusters with multiple servers. But what does declarative mean? Let's have a look at a typical deployment. A deployment is one of the many Kubernetes kinds, a resource type. These resources are typically written in YAML format and then posted to the cluster with the kubectl command line tool. Under the hood, kubectl just uses REST for communicating with the Kubernetes API server, for creating, updating and deleting resources. A resource always consists of these three parts. The first part is the metadata. The most important information in the metadata is the unique name of the resource. But there are many more, which I'm skipping here for simplicity. The next part is the spec. Here you specify details about what this deployment should look like. Deployments are always about pods. A pod is a kind, so a resource type on its own, but typically embedded in a deployment, just like here. The pod then consists of one or more containers, and the most important part of a container is which image to use when running it. Another field of the deployment spec is replicas, which declares how many instances of the pod you want to run in your cluster. Example given for high availability or scaling reasons. So, what happens when you create this deployment? I already mentioned the API server, but there are more core Kubernetes components running in the cluster. One of them is the controller manager. The controller manager is watching for deployment resources and compares the spec part of the deployment with the current state in the cluster. When it, example given, sees that the spec declares 2 replicas of a pod, but none is running yet, it will create 2 new pod resources. When a pod is deleted by someone, it will recreate the pod. When the replica field is updated from 2 to 1, it will delete a pod itself. So basically, every time the resource or the cluster changes, the controller's so-called reconcile function is triggered, which tries to update the cluster until it matches the spec. The next component is the scheduler. It watches for new pods and assigns them to a node. For this it uses memory and CPU requirements, which you can specify on the pod, and free memory and CPU resources on the nodes. At this point we still do not run anything. We just have a bunch of Kubernetes resources. This is where the kubelet enters the game. Kubelet is a component running on every node. It watches for pods which are assigned to the node it is running on, and it starts or stops the containers of those pods. Our workload is finally running now. The last thing happening now is the third and last part of the deployment resource is updated with status. This is an informative part for users. Similar to this deployment, there are many other core Kubernetes kinds. For example, daemon threads for running workloads on every node, jobs for running short-lived tasks, services for declaring network connections, and several kinds about data persistence. All these kinds already give you a quite powerful way for declaring your workloads. But there is a drawback. If you, example given, want to deploy a database, not once only, but regularly, you need to create multiple resources each time. The deployment and all the network and persistence related resources. Wouldn't it be easier when users just have to create a database resource? Luckily, this is possible. You can declare your own new kinds with so-called custom resource definitions. They tell the cluster how the spec and status parts of your own kind have to look like. But CRDs alone would not do anything yet. You also have to implement your own controller, which reconciles instances of your custom type. For the database example, this controller would then create the deployment and configure network and storage automatically. This bundle of one or more CRDs and their controllers are called operators. So let's get to the actual topic of this session, Medik8s. Which problems does it solve? While failed containers are already restarted by core Kubernetes components, the situation gets more interesting when a complete node has issues. The kernel can freeze or hardware dies. It gets even more interesting when the workloads on the node require at most once semantics, because running multiple instances configured with the same storage would potentially result in data corruption or data loss. This means that we need to ensure that the workload on the failed node is stopped. This is called fencing. The next problem is to restart the workload on a healthy node as fast as possible. Kubernetes will only restart workloads when it knows that they are not running anymore. For unresponsive nodes, this might never happen automatically, because the pod status will be unknown forever. An administrator would have to check the cluster manually and delete the node resource or the pod resources. No question that this is slow. Medik8s aims to automate this process, which is known as remediation. Last but not least, ideally, the failed node should be recovered as well, in order to restore compute capacity. How does Medik8s deal with these topics? We split the problem into two parts. The first one is about failure detection. How do we know that we have a failed node? The second part is fencing and remediation. How do we safely recover workloads and ideally also recover the node itself? Let's start with failure detection. This is handled by the node health check operator. From Kubernetes point of view, nodes are just resources, just like everything else. That means that nodes can be retrieved from the API server, and the status part provides information about the health state of the node. The node health check operator can be configured to watch this status, and it takes action when something indicates a failed node. The default configuration is looking for the so-called ready condition of the node status and considers the node to be failed when this condition is not true for more than 5 minutes. When this happens, the node health check operator will create a remediation custom resource. The health check configuration contains a template for this remediation resource, so basically it can be anything. This way we have a kind of plugin system. By default, the health check is configured to create a remediation resource which is owned by the Selfnode remediation operator. The Selfnode remediation operator is the second Medik8s component I'd like to introduce today. The operator deploys a Kubernetes daemon set which is running the Selfnode remediation agent on each node. These agents watch for those remediation resources created by the node health check operator. Once such a resource is found, the agent on the affected node will fence it. The safest way for fencing is to power off or reboot the node. Since we also want to potentially restore compute capacity, we try a reboot. The safest way to do this is using a watchdog. Once the Selfnode remediation agent starts on the node, it will initialize a watchdog and regularly feed it. Once a remediation CR is detected, it will stop feeding, and after a short timeout, the watchdog will reboot the node. As a fallback, it is also possible to allow software reboots in case of issues with the watchdog. The next step is remediation. We want our workloads to be recovered on healthy nodes as quickly as possible. For indicating to Kubernetes that it's safe now to reschedule and restart pods, because they are already fenced, Selfnode remediation will force delete the pods and their volume attachments on the affected node. The latter is a part of the storage configuration and binds storage to a specific pod. Ideally, the reboot also solved the issues on the failed node, so that compute capacity is restored as well. But we have two problems with this approach. Number one, in case of issues with the network connection to the API server, how does the Selfnode remediation agent know about the remediation CRs? Solution: it will ask the agents on the other nodes if they see a remediation CR. If they respond positive, or if the other agents can't be reached as well, the node will be rebooted. Problem 2. The agent might not run anymore on the failed node. Solution: the watchdog was armed when the agent started, and it will trigger a reboot when the agent pod is forcefully killed. Note: a graceful stop of the agent will disarm the watchdog before exiting. This means Selfnode remediation can also be used standalone. It provides basic functionality even without remediation CRs. But standalone, you have less configuration options compared to running in combination with node health check operator. So let's continue with a demo. The first question is how to install node health check operator and the Selfnode remediation operator. For this, you can use operator hub.io. At the moment of recording this, the node health check operator is a bit outdated, and the Selfnode remediation operator does not even exist already on operator hub.io. But in September, both will be available. So let's have a look at the node health check operator. Search for node health, and it already pops up. Then you click on install, and it provides instructions on how to install the operator lifecycle manager if needed, and how to install the node health check operator. So for the actual demo, I prepared a cluster where both node health check and Selfnode remediation operators are already installed. Let's have a quick look at their pods. Here you see two controller manager pods, one for the node health check operator and one for Selfnode remediation operator, and three more pods. Those are the agents of Selfnode remediation running one on each worker node. At the moment we have the limitation that Selfnode remediation only works on worker nodes. We are going to update this for the next release. Next, let's have a quick look at our demo deployment. So here we see that it's running on node worker 2. Let's keep this in mind. Then I want to have a look at the node health check configuration. Here we see, like I explained earlier, we first have the metadata, which with the name NHC worker default. Then the spec part, where we see one field min healthy. This means when we have less healthy nodes in the cluster than declared here, we stop remediating, because then we probably have a bigger issue in the cluster and just rebooting things won't help anymore, and we might even make it worse. So then the next thing is the remediation template. This is the plugin system I try to explain. Here you can say what kind of remediation resource to create when a node is unhealthy. Then we have a selector. Since we know that Selfnode remediation is limited to worker nodes, we also configure a node health check operator to only look for worker nodes. And last but not least, we see the unhealthy conditions in the spec. For this demo, I decrease values a bit, the timeouts. This means then when the ready condition of the node is false or unknown for 1 minute, then we consider the node as unhealthy. Then we also have a status section. Here we see one condition, which is explaining that node health check is not disabled. It is currently looking at 3 nodes, and all 3 of them are healthy. And more human readable form is face and reason, which is just saying that everything is fine at the moment and we have no ongoing remediation. So on the top right, we will monitor exactly this status section of the node health check configuration. On the top left, we see the nodes and have a look at the status here. And it will also display later on the remediation CRs as soon as it's created by node health check. So for simulating a failed node, I will now log in to the worker 2 node. Just to make sure, yeah, this is worker 2. And I will just stop kubelet and this will make the node not ready, as we will see soonish in the top left. In the meanwhile, we can start monitoring our test deployment. And now we need to wait until the node gets not ready. Here we are. Worker 2 is reporting not ready. So this is where node health check starts taking the time until the 60 seconds from the configuration are fulfilled. Fast forwarding a bit, we see now on the top right in-flight remediations in the node health check configuration, which is saying worker 2 started remediating. We also see healthy nodes was decreased to 2. And we also see phase and reason, it's remediating 1 node. What we also see on the left side, the Selfnode remediation custom resource for the worker 2 node. We also see that scheduling was disabled for the node. On the bottom, we see that the pod was already deleted and a new pod is already running on the new node worker 1. And after some more time, complete remediation has finished, everything is cleaned up. We have a ready worker 2 node. The test deployment is running on worker 1. And the node health check status is reporting that everything is fine. 3 healthy nodes, no ongoing remediation. Just to show that the node was actually rebooted, let's have a look. Uptime 3 minutes, so it was just rebooted. That's it for the demo. And this also concludes my presentation. In case you have any questions, feel free to find more information on our website Medik8s.io. You will find all the source code of our components on github.com/Medik8s. You can find me on site at ContainerDays.io, or you can reach out to our Google group on the Google group website or via email on Medik8s@googlegroups.com. Thanks for listening. Goodbye.